Okay, good evening, everyone. The paper I present today is the heterofederated learning, and the author comes from the Duke University. The paper is published in ICLR 2021. Okay, the first part is the motivation. In today, mobile devices and the IoT devices are becoming the primary computing resource, and they can produce a significant amount of data. In this environment, because of these devices' growing computational capabilities, it becomes increasingly attractive to store data and train models locally. So here we use the federated learning. But for the existing federated learning, the global model has the same architecture with the local model. And in fact, the client in the federated learning can vary different significantly, and the computation and the communication capabilities of each client devices may vary significantly. So here's the problem of here is the heterogeneous problem. So in this paper, the author proposed that do the local models must share the same architecture as the global model, and thus they proposed this paper, heterofederated learning. The heterofederated learning can train heterogeneous local models with varying computation complexities and still produce a single global inference model. Okay, the next part is the design part of the heterofederated learning. And the main idea of this paper is to decide the parameter size for different clients according to their computation complexities and communication abilities. And thus, in the aggregation rules, this paper can let the smaller local model have the same influence on the global model. And in this figure, you can see the block represent the set of parameters, and the blue block means a small set of parameters, and the red block means a large set of parameters. Okay. And to reduce the computation and the communication complexity, we can consider local models to have similar architecture, but can shrink their complexity within the same model class. And in this paper, the authors consider local model parameters to be a subset of the global model parameters. Means the WI means the client I. WI is a subset of the WG. WG is the global model. And to reduce the size of deep neural network, the author choose to vary the width of hidden channels. By reducing the number of channels in the hidden layer, the computation complexity can be reduced, and the local model and the global model architectures are in the same model classes, and to stabilize the global model aggregation. Okay, in this algorithm, we can select subsets of the global model parameters WL for a single hidden layer. And the WL is a subset of the WG. WG means the global model, and the DG means the output output channel size, and the kg means the input channel size. And in this paper, the author set P computation complexity levels. And for example, the WLP means the local model with the less computation complexity level, and the WL1 means the local model with the highest complexity level. And let R be the hidden shrinkage ratio, so we can get the DLP and the KLP. The D and K are the output and input channel size of the layer. In that assumption, so we can compute the size of the local model parameters and also the model shrinkage ratio. Here we can get the aggregation rule. You can see the WLP means the local model with the lowest computation complexity level, and it's a subset of the WLP minus 1, and the WLP minus 1 slash WLP means the parameter elements included in the WLP minus 1, but excluded in WLP. So in that case, we can aggregate the global model. You can see the first equation shows the smallest part of the model parameters, and it is aggregated from the local clients that contain it. In the figure, it's the blue block, and the P is 3. And in the second part of the equation 1, the set difference between the part P minus 1 is the orange block, and the blue block of the model parameters is aggregated from local clients with computation complexity level. And in the aggregation rules, the global model parameters WG is constructed from the union of all of the disjoint sets of the partition. So using this aggregation rules, the local model with nice parameters can also have the same influence on the global model with the compared with the larger set of parameters. Any questions?
Paula, are you there? I think probably she presented this paper in our own seminar before.
Oh.
Yes, yeah. Machion presented this paper before, yeah.
Before in our group meeting, right? Oh, okay, okay. Yeah, but Honglu, I do have a question. So basically this one, because I listened to this similar presentation before, I'm kind of understand this paper, but I'm trying to figure out, when you determine the WL3, for example, the size of the blue one, the orange one, and the red one, which is the dominant factor you consider? You consider the computing capability of the device, or you consider the, say, the channel, the bandwidth, or say the wireless resources for a certain kind of device? Which one is going to determine you choose which size of this kind of parameters?
In this paper, the author considered the computation abilities, and I think in his experiments, they just decide the complexity levels to set the complexity levels such as the 0.50 0.25.
But basically, the determining factor will be the computing capability of the device, right?
Yeah.
Because there should be I don't know, there should be a minimum function of computing capability and communication capability. For example, your communication capability allow you to transmit how big local model app is, right? And also say your you train how big model, right? So you choose the smaller size of both, right? And, in this case, so you can decide, what kind of what kind of size of WLP, right?
Mm-hmm.
You got my point, right? So, but I think this one they only vary the computing capabilities, right?
Mm-hmm. Yeah.
Oh, okay.
So in this paper, I think the author thinks the devices with less computation ability can train a local model with less parameters.
Yeah, I got the point, but the reality is sometimes, certain kind of device, they have very limited computing capability, but they have very good channel conditions, right?
Mm-hmm.
Certain conditions, their transmission condition, the channel condition is very bad, but their computing capability actually is okay, right? So I understand it's there's a very theoretical paper, probably they didn't consider much about practical engineering factors. They only reduce the overall computation complexity of the model so that they think they can reduce both the communication and the computation costs. That's true, but yeah, it's I just try to figure out, in practice, how can we use this kind of paper, right? So
yeah, I think this paper is in the very beginning phase, and there are some problems here.
Okay.
Dr. Pan, what do you mean by the communication channels here?
Just like transmission rate, data rate, how big a transmission data rate you can have. Sometimes your channel condition is very bad. For example, let's say outdoor environment, your transmission delay is a lot, or fading is big or something.
Yeah. I think this paper just reduce the size of the model. Then they said they can improve the communication efficiency, but they didn't care about, they didn't discuss the physical world communication issues, right?
Exactly. By reduce the model size, you can reduce both, right? You can reduce both computation and communication. But I try to figure out, what's the major determining factor? Because in reality, there will be case sometimes your transmission is good, but your computing capability is limited, right? So
I see.
Yeah.
So I mean, if we wanted to, for example, if we have enough computation capacity, but the communication quality is not good enough, then we probably can try some network coding to trade communication quality for computation.
That's true, but I don't think that's much advanced solutions. But if we based on this paper, if their computing capability is good, but the channel condition is bad, like you mentioned, I think the communication part will be the bottleneck. In other words, that will be the dominant factor. You need to consider how big the model size you should choose, right? So yeah.
But do you have some
yeah,
please go ahead.
Yeah, our group have several papers. We have one Infocom very initial papers discuss that. I think Ray is not here because she got the booster yesterday, so she didn't feel well today. Yeah, she write a few papers, and I think Pauna have some draft about this kind of a communication and computation trade-off paper. Yeah.
Can you give like an example about a device with very high computation capacity but very poor communication quality?
Yeah, there are multiple possibilities. For example, if your device only have 4G network access, right? So in practice, 4G uplink transmission rate is like 4 to 10 Mbps, right? But device 4G something, and you can do some on-device training or whatever. You have enough computing resources, but you have very limited communication resources, right? So vice versa. So for example, you have certain kind of simple device like what I have with the iPhone 11. You know, you can do certain kind of on-device training, but it's very limited. But if I subscribe to 5G network, so you can boost your communication capability a lot. For example, you can have like a 30 Mbps, you know, uplink rate, something like that. So yeah, that's kind of examples, you know, in practice. Yeah,
I see. Yeah, as what I thought, like previously, I thought like most problems in IoT and in like a wireless scenarios is like the computation capacity is not good enough, but the communication is okay.
No, I think most, because if you check the literature, right, there's a lot of communication efficient FEL learning papers.
I see.
Right.
Okay.
They consider communication will be the bottleneck. I think their assumption is, you know, nowadays, even for the internet, you know, the uplink transmission rate is kind of limited. Their assumption is less than 8 Mbps. So the communication will be dominant. But if you consider 5G, you know, Wi-Fi 5, Wi-Fi 6, you know, indoor, this kind of communication, the transmission rate will be very high. Yeah, much higher. So in that case, if your model size is not very, very big, it's not huge, then communication is not necessary to be the bottleneck. Sometimes the computing will be the bottleneck. Yeah.
I see. Yeah, that makes sense. I think there are different scenarios. And the scenarios you mentioned, I think the do exist.
Yeah. We do have a magazine paper. I think, Dan, could you share the magazine paper afterwards with the group?
Okay, sure.
Yeah, Dan write a magazine paper to discuss that. Yeah, the communication and computing trade-off.
Yeah, we probably can think about like how to you know deal with the communication quality, probably from the model level, from the aggregation algorithm level. Yeah,
we can extend this paper for sure, but I'm not sure that's kind of incremental or not. But definitely we can, you know, put their algorithm into practice.
Okay. Yeah.
Okay, thank you, Honglu. Thank you, Dr. Wang.
Thank you. Okay, let's continue. In the next part, the author want to use the batch normalization in the heterofederated learning, and the batch normalization can facilitate and stabilize the optimization. And we can add a batch normalization layer after the input layer to do normalization tests to improve the learning rate and to solve the problem that data distribution in the middle layer may change during training. However, classical federated average on most of the recent federated learning works avoid batch normalization. The major concern of the batch normalization is that it requires running estimates of the data representation at every hidden layer, which can, when we uploading these batch normalization statistics to the server, there will be higher communication costs and also the privacy issues. So in this paper, the author proposed the static batch normalization model. In the SBN, during the training phase, the SBN does not track running estimates and simply normalize the batch data. And after the training process, the server will query local clients and update the global batch normalization statistics. So it can solve the problems I referred before. And the third part of the design is a scalar. Because we need to optimize local models for multiple epochs, and the local model parameters at different computation complexity levels will digress to various scales. And to directly use the model during the inference phase without scaling, we need to use the dropout, for example, the inverted dropout. But in this paper, because the Federated learning can directly select the subnetworks from the subnets of the global model parameters. So we can append a scalar module right after the parametric layer and before the SBN and the activation layers. So we can directly use the model during the inference phase without scaling. And based on the SBN scalar, a typical linear hidden layer used in the HeteroFederated learning framework can be formulated as the equation. The Y means the output of the layer, and the WMP means the parameters for the client M, which has the computation complexity level P, and the B is the bias, X is the input. Okay, and the next part is the evaluation. In the experiments, the author chose 3 models, for example, the CNN, the transformer, and they are based on 3 data sets. And here is the data partition. For IID data partition, the author assigned the same number of data examples for each client. And for balanced non-IID data partition, the author assumes that the label distribution is screwed. And the authors set 5 computation complexity levels, A, B, C, D, E, and this complexity level 0.5, 0.25, and so on. It means the model in B complexity levels has half parameter than the model with complexity level A. And the authors also designed the fixed experiments and the dynamic experiments. In the fixed experiments, they have a fixed assignment of computation complexity levels. And in dynamic experiments, the local clients uniformly sampling computation complexity levels at each communication round. And this figure is based on the fixed experiments. The AB means we can change the number of model parameters by change the partition of the model with computation complexity A and B. For example, when the X is 1, it means all of the model has the computation complexity of level of A. And when the partition of B increase, the value of X will be smaller. And this figure can show the effectiveness of the heterofederated learning. And the later experiments are dynamic experiments. In this table, the ABCDE means the local model includes all of the 5 computation complexity levels. And there are 3 baselines, including the LG federated average and the original federated average. You can see using the heterofederated learning, the parameter size can be smaller and with higher accuracy. And here's the experiments based on the different data sets.
Honglu, could you go to previous page, the big table? Yeah. For the first row, the global accuracy is for non-ID. Oh, okay. For ID cases, always you use the full size is the best, right? Oh, for non-ID case, okay, you use the full size is not necessary to be the best. Oh, okay. I just try to catch that part.
Okay.
Yeah, because in my mind, I think if you use the full size, you always have the best results. Oh, okay. I just want. So for non-ID case, even you use the full size, it's not necessary you have the best testing accuracy, right? Or training accuracy. The testing accuracy. If you check the last column, first row and second row. If you use the full size, yeah, the performance is a little bit worse than you use A2E.
Yeah.
So that's the testing accuracy or training accuracy?
Let me check. Oh, it's the testing accuracy.
That's the testing accuracy, right? So for C's case, it's the same. The third rows, the third group, I would say. Say C2E, C2E also have the best performance. Yeah. Also, it's for ID case, it has the best performance too. C2E, you have certain kind of, I don't know, you have a certain kind of sample, right? You don't use the full size of the local model updates. Why its performance is better? It's a little bit better. Well, this is comparable. Do they justify that? Because according to my understanding, probably use the full size to do the training. You consume more computing and communication resources. You're supposed to have the best performance. Well, never mind, because their performance is very close. Yeah.
I think the author only mentioned that the C2E is very close to the C, and don't explain why the C2E is better.
Yeah. For the testing accuracy, anything can happen. Also, it's very close, so no big deal. Yeah. Okay. Thank you then. But CDE is also better than C.
Yeah.
Yeah. It's very close though, but It's weird. Okay. All right, thank you then.
Okay. Okay, here's the hyperparameters and the model architecture used in the experiment. Oh, I forgot.
Is it like a general phenomenon that the C2E, CDE is better than C? Is it a general one? So for all the cases, if
Yeah.
so CDE and CE is better than C, right? For all the cases.
Yeah.
For non-ID.
Yeah.
The local, but the global is not okay. Okay, the global is for both global and local. They're better than the C case, right?
Mm-hmm.
Also for ID, ID is worse. Yeah.
Right, ID is worse. Any chance? I mean, because of this kind of the local model use a subset of parameters, right? Any chance can be helpful to improve the personalization of the local model, then eventually improve the global model. Do you think? Because now, I mean, for different, so originally, if we see like the model, like the case C, right? Then every client are using the same model size, right?
Yeah.
But for CE or CDE, then different client may have different model sizes.
Because these experiments are dynamic, so I think maybe the CE can maintain more personalized information.
I don't know. Yeah. They don't explain this issue, right?
Yeah.
Okay. Okay, I think that's interesting, but you can continue.
Okay.
Thank you.
And in the next experiments, the author compares the effectiveness of the SBN with other normalization methods. Yeah. I think the last part is the discussion. And in the SBN, the author proposed that because the server need to query all of the clients to get the statistics, so there may exist privacy concerns. And the author mentioned that maybe it will be solved in the future work. Okay, that's all. Thank you.
Yeah, can you stop the recording?
Mm-hmm. Okay.